Hi, my name's Stone. We already did this last week, but figured I'd reintroduce myself. I figured we would start with the fun little questions to make it so we don't have to get into really dense topics right away. So, the table topics, people. Josh and Ryan. Which one of y'all wants to go first?
I'll go first.
Okay, see. You get the fun one. Yeah. I can find it. Alright, so, my question, very topical. ChatGPT. So that ChatGPT is obviously getting more and more impressive, honestly, and all the AI stuff like that. So I wanted to get your thoughts on the use of it, not in like an academic sense where you're being graded on this work, but just in research or in a professional sense where you might just be using it as a tool.
Okay. Okay, so my name's Joshua Bridges, and I wasn't here first week. So the question was, how do I feel about ChatGPT in an academic sense, not necessarily for doing the assignment? So I feel like there's pros and cons to it, obviously. ChatGPT, like everyone knows, it learns from the stuff you tell it. So if you keep asking it certain questions, it will answer with whatever the questions that you specified or that you've given to it, and it learns from what you tell it. So it can be helpful in some sense as long as you aren't necessarily giving it the wrong intel. So I believe whenever you use it to research stuff, it could be helpful in gaining a more broad sense of knowledge regarding the topic you're on, but I don't necessarily think it's the most accurate, and it's obviously shouldn't be used as like a source or anything like that. You shouldn't use that as a source. But I do feel that if you use it to kind of gain like an idea and then research more on the topics that they bring to you, like for instance, you can ask it to I don't know, as a Toastmaster, give me 10 engineering questions. Right?
Would have been a good idea.
If you do to that, then it can give you an idea of some questions, and then you can look more into developing and expanding your knowledge on those questions, or just in general academic research way. That's what I
All right. So I just wanted to get your opinion on, is there some kind of like moral responsibility for us as engineers after we graduate to continue learning about a bunch of stuff? Or is it fine for us to just use what we've gotten up until that point and just use that?
So just talking about learning as far as the
Yeah,
moral
just
side.
do you feel we have to continue learning as engineers?
My name's Ryan Purvis. I'm a 5th year senior. I was the cameraman last week, so I didn't have to do any of this. The question was, what's the moral implications of having to continue your learning after you graduate school? I think you definitely have a moral obligation to continue learning, because it's what life is. It's constantly learning stuff. Technology doesn't stop just because you've graduated 10 years ago. New technology is always coming out. Things that you haven't learned in class. We take a very generalized approach, I'd say, to engineering. Once you get into your career, you might want to do something much more specialized, like something in aerospace. And so to effectively conquer those challenges, you have to know what you got to know to be able to do that. And if you don't, then you'll be looking like a 747 Max and crash. And that's why you should continue learning. Thank you.
Thank you.
Okay. My name is Alan Thurman. I'm presenting on the thermocouple time constant experiment. So, background for this experiment is to investigate the effects of transient heat transfer on the use of a thermocouple, which is just a thermal measurement device that uses thermoelectric effects to generate voltage dependent on temperature. Some applications of thermocouples are for the food and beverage industry, such as like refrigerators and ovens, that sort of thing. Metal foundries, you can make thermocouples that have pretty high temperature resistance, so it's really good for high temperature applications. And then additive manufacturing is probably a place where a lot of you have seen them in like the heated beds and the extruders of 3D printers is a very common application. The primary governing physics behind the transient heat transfer for thermocouples is the lump capacitance model, where you consider it as basically having no thermal resistance inside of it because it has a much higher thermal conductivity than the heat transfer coefficient, i.e. the Biot number, the ratio of convection to conduction is much less than 1, as you can see in this diagram. You can see that the thermal gradient, whenever the Biot number is very small, is minimal. So you can assume that it's not, and then you can do a basic energy balance where you take energy accumulated and equate it to convective heat transfer, and then whenever you solve that differential equation, you can get the equation on the left, and then that you can derive for the time constant, which is dependent on the convective heat transfer coefficient, the surface area, density, specific heat capacity, and volume. And then you can see on the right some differing effects from the time constant depending on whether it's greater than or less than 1. So the experimental apparatus for this experiment, we're going to have a beaker of boiling water, a hot plate, a beaker of ice water, and then a computer running a data acquisition software for the thermocouples. And then you have the thermocouple itself right here. So the procedure for this lab is fairly straightforward. You're going to open the DAC software on the computer in the lab. You're going to fill a beaker about half full with water, either ice water or then you will either add ice or put it on a hot plate, depending on which part of the lab you are assigned. Then you'll connect the K-type thermocouple to the plug on the computer, confirm it's configured properly, and then you'll perform a test run to check the transient response, make sure that it's behaving properly, just inserting it into the water, removing it to make sure that you're seeing a transient response. And then once the thermocouple has been verified, you'll begin data logging the data in the DAC, and then you'll insert the probe quickly into the beaker, whichever ice or hot water that you have. Wait for it to get up to the expected temperature 0 or 100 C, depending on which one you have. And then you will carefully remove it, wipe it off, and then make sure to hold it still so you don't induce any convective effects, and then wait for the temperature to stabilize back to room temperature. And then you will do the same thing in the opposite direction and data log that as well. And then some expected results for this experiment. So you're expected to produce plots of temperature versus time, plots of time versus the log of normalized temperature, normalized temperature versus time, and then all the plots for both boiling and ice water. So depending on which one you had, you will have to get the data from the other people in the lab and share that, and then collaborate to generate the plots for both of those. And then you can see some expected characteristics of log of normalized temperature versus time, and then normalized temperature versus time on the left. I didn't have any data sheets on the thermocouple itself, so I couldn't generate like what you would expect to see from the hardware in the lab, but I tried to do my best with what I had. That's all.
Hold up. So apparently we have to hold some questions. So, anybody got some questions on the thermocouples? Yeah.
Can you explain the Biot number thing again?
Yeah, the Biot number.
Yeah.
So the Biot number is a dimensionless number used in heat transfer, and it's the ratio of convective heat transfer to conductive heat transfer. So if you have a very small Biot number, that means that your denominator is much larger than your numerator, making it much less than 1, which indicates that you have such strong conductive effects that compared to your convective,
that you're effectively a uniform temperature across with like a change in temperature on the outside of the body.
Alright. Let's do it. You're free to go.
Okay.
No, I have a question.
Oh, sorry.
Have you done a retransfer course before?
Yes.
Yes, okay. So is the Biot number the only requirement for the lumped heat capacities method, or is there another requirement for it?
I think it's supposed to be relatively one-dimensional. So you have like a non-uniform body. Like if you had, I don't know, like your thermocouple was shaped like a T at the end, and there was some like two-dimensional effects going into play that could be an issue.
Now, in terms of a dimensionless number like the Biot number, is there anything else?
Not that I can remember.
Something called the Fourier number, which depends on your dimensionless
The
time
Fourier-
constant.
Yeah, the Fourier number is your time constant, right?
Yeah, but it has to also be less than 0.2 for you to work, for this to work.
Oh, okay.
Okay.